Hi everyone, here's a little capacitor review, getting ready for the AP test. And so remember, with capacitors we're going to deal with parallel plate capacitors. And parallel plate capacitors, you hook them up to a battery and we have that charge separation. So on the positive plate we're going to end up with positive charge that's connected to the positive terminal on the battery. We're going to have an equal amount of negative charge there, and we can call that that's going to have an EMF associated with it. Now if we take this and we kind of expand it and we look at the two plates of the capacitor in some detail, the charge is going to reside on the inner surfaces of these. If you think about it, these are made of conducting material. And so these opposite charges are going to be attracted to each other, and so they're going to be, and conductors are free to move around, so they're going to be on those inner surfaces there. And remember that we have charge Q on the capacitor, and that's going to be equal to the charge on each plate. So each plate has a charge Q. Okay, so this is going to have a charge positive Q, and this is going to have a charge of negative Q. Okay, so what I want to do is I want to derive the capacitance for the parallel plate, but let me mention one more thing before that. So we know with these parallel plates we get this nice uniform electric field here. So we're going to have the electric field is going to be represented by these nice parallel lines moving away from positive and toward negative. So that's our E field. Okay, and this derivation is going to use a couple different things that'll be good to review. So the first is Gauss's law. Okay, so we have to think of a Gaussian surface. So what we want to do is we want to draw a Gaussian surface so that we have, the electric field is going to intercept at least one part of the surface, if not more, so that we have some electric flux, because we know that the flux is equal to the enclosed charge over epsilon naught. So we have to decide what the Gaussian surface should be. Now if you think about this plate, it looks like a rectangle here, but remember it goes into and out of the page as well. So for our Gaussian surface is going to be a rectangular prism, otherwise known as a box. And so what we're going to do is we're going to imagine this rectangular prism going there. It's going to go down. Okay, and I specifically put this edge inside conducting material. Okay, we know that inside this conducting material there's no electric field, and then the bottom edge is between the plates. Okay. And basically we want this, if you think of the plate going into and out of the page, we want the Gaussian surface to extend the same as the plate. Okay, so the rectangular prism encloses the whole bottom surface. And the reason why we want to do that is because that means that finding Q enclosed is going to be really easy. Okay, so when we do that, it's good if you're doing a Gauss's law problem to specify what your Gaussian surface is. Okay, then we're going to say that the flux, remember this is the electric flux, is equal to E dot dA. That's going to equal Q enclosed over epsilon naught. Okay, and so when we look at this, the flux is really easy. So the top is going to have no flux, the sides are going to have no flux. It's only the bottom that has flux. So we've got the E dot dA, it just becomes E times A, and A is the area of this plate. So we choose that. Remember, with the Gaussian surface you get to decide what it is. Now Q enclosed well, if we look at this, that's just the charge on the plate that we just called Q. So we're going to say that's Q over epsilon naught. Okay? And so our formula for the electric field is really simple. So E is equal to Q over epsilon naught A. All right, so that's one part of it, but we want to get to capacitance. Okay? So as we go to capacitance, we need to find the potential difference between the plates, because we know that capacitance is defined as the charge per volt. Okay, so we know that the capacitance is equal to the charge per volt, V being the potential difference between the plates. Okay, so we've got Q already, and we can get V from E. So we also know that the potential difference is equal to minus the integral of E dot, I'll use the vector notation. I'm going to use dx. Sometimes I think on the formula sheet you might see dr or dx. Your book uses ds, all sorts of things, but let me define what x is. So we need a distance. Okay, so we have our two parallel plates. We've got the electric field, which points downward. Okay, and so I'm going to say x is actually going vertically, so that's 0, so it's kind of like on the number line. That is x. Okay, and remember, we always specify this dimension as d, the distance between the plates. Okay, so our potential difference is equal to minus the integral. E, we just saw, is equal to Q over epsilon naught A, and dx. Now we need our limits of integration. Well, x goes from 0 to d, so that's pretty simple. Okay, so this is, as some of my college professors would say, it's basically a trivial integral to do, very easy. So delta V is equal to minus, because Q and epsilon naught and A are all constants, so the integral of dx is just x. Evaluate that from 0 to d, so we get minus Q d over epsilon naught A. Okay, now we've got this delta, so we've got this issue here of here we've got delta V. This doesn't have the delta in it, but when we talk about the voltage across a capacitor, we're talking about the potential difference between the plates. So we've got notation issues. The other question is the negative sign. Well, the fact is that when we find the potential difference, again, we're not worried about which is the top plate and which is the bottom plate and which is positive and which is negative. So the potential difference, we aren't worried about that sign. Okay, so I'm going to rewrite this, and I'm going to drop the delta on the left side, and I'm going to drop the negative sign on the right side. So the potential difference across the capacitor is just Q d over epsilon naught A. Okay, and then for our last thing here, we're going to put this together. Okay, and so the capacitance, remember, is our capacitance is equal to Q over V. So I'm going to solve this. I'm going to get Q over V on one side. So if we have Q over V on one side, that would leave us with epsilon naught A over D on the other side. And so if you remember our formula for capacitance, that's what we have, epsilon naught A over D. Okay. So that's something, if they ask you to derive an electric field in a capacitor, that's the strategy. We use Gauss's law. And so you just choose your Gaussian surface correctly there. A couple other things about capacitors really quickly. A dielectric, when you insert a dielectric, remember the dielectric always increases the capacitance. Always, always, always increases the capacitance. Okay? So they tend to have two kinds of questions with the dielectrics. One is with the voltage held constant. So they're going to keep this connected to the battery. And so the question is, so this is going to be Q, and we're going to have a, so the voltage of the battery is going to equal, after you let this charge up completely, that's going to be our voltage. So if we hold the voltage constant, so if we take our dielectric and we put it in here now, what's going to happen? Okay, so we know the capacitance is equal to Q over V. Okay, we put the dielectric in there. If the capacitance is going to go up and the voltage stays constant, that means that the charge increases. So if this Q is like, once you put the dielectric in there, you're going to get more charge on there. Okay, but the voltage stays the same. Okay. The other thing that happens is they keep the charge constant. So we'll charge this thing up. It'll have Q there on there, and then what they'll say is, oh, we're going to disconnect it from the battery. Okay, so the Q is still there, and then we're going to put a dielectric in. Okay, and so if we look at this, something is going to stay the same and something's going to change. Well, once they disconnect it from the battery, there's nowhere for charge to go. So that means the Q stays the same. So if charge is held constant, we're going to have the same amount of charge on there the whole time. I'm not going to do the negative plate. You get the idea. So that charge is still Q, still Q. Okay. So if we put the dielectric in there, and now we hook up a voltmeter and measure the potential difference there, again, the capacitance is equal to Q over V. So if Q remains the same and the capacitance has to increase with the dielectric, then that means the voltage decreases. So that's kind of a conceptual type question, okay, but that could be, it's an easy thing to do in a capacitor problem, is to have you do some things related to the capacitor and then look at the effect of adding the dielectric on there. Okay, and remember in the equations they're really all about that. So remember we just did the capacitance. Remember on the formula sheet we said it was epsilon naught A over D. Well, remember it's really kappa epsilon naught A over D. Okay, if air, remember the dielectric constant kappa is K, that is the dielectric constant. So for air it's 1. For anything else, any other material, it's going to be something greater than 1. So it's going to increase capacitance. And then just a quick note about capacitors in circuits. A couple weeks ago we did a pretty thorough circuit review which included RC circuits, so I'm not going to go into the RC circuits again. But remember, when we're talking about capacitors in series circuits, so we have our EMF, we've got our capacitors C1, C2, and C3. Okay. So the big thing you want to remember is that the charge is the same on each capacitor. So that means Q1 has to equal Q2, which has to equal Q3. Okay, they are all the same, regardless. And so what that means is if we have different capacitances, that if the charge is all the same but the capacitance is different, that means the voltages can be different. Okay. And remember, the loop rule always applies. So that EMF minus the voltage across C1. So if we use the loop rule, we would know that the EMF would have to equal V1 plus V2 plus V3. Those three voltages added together. Okay. Now for parallel circuits, sorry, I forgot to put the label there. Then what we know is that the voltages is the same on each capacitor. So we can call this C1, C2, and C3. So we know that V1 has to equal V2, which has to equal V3. And if it's been charging for a long time, then that would be equal to the EMF of the battery. Okay. But again, since capacitance is charge over voltage, and if the capacitances are different, that means the charges can be different. So the charges can be different. Okay. All right, so that completes our little review of capacitors.